Hello everyone, welcome to the last lecture of our course. I hope you all have enjoyed this course a lot. So, in the last few lectures, we have been doing numerical computations, and in this lecture, we will complete our learnings of numerical computations by looking at integrations. Okay, so the main goal of this lecture will be to do numerical integrations. And towards the end, I will also do a ODE solving problem. The problem that I will choose will be slightly advanced. But if you have followed all the lectures carefully and actually have typed those code in your PC, you have practiced those things, then it will not be a hurdle for you guys. But if you have just been watching the lectures and haven't done any coding, then you might get a bit overwhelmed by those problems and you might get stuck at locations. Okay, but we'll look at that later. For now, let me write the goals of today's lecture. So we will look at numerical integrations, how to do them. Like previous lectures also, we will do coding from scratch. We will also verify our results with known answers. And we will also look at some functions from this package called integrals.jl, which is again another Julia package, which gives you some written functions to perform different kind of integrations. Okay, and finally, we will solve a ODE problem. By ODE, I mean ordinary differential equation solving. And what that problem will be is a surprise for now. Okay, so the package that I will be talking about later is this integrals.jl, and I have already opened the documentation of this package. So you can start using it like this, and you can go to the tutorial of this package also. So here is the GitHub page. So it says that this is a instantiation of this SciML common integral problem, and these interfaces common numerical integration methods and packages for Julia. And essentially, this what this can do is this can calculate the results of numerical integrations via different methods. So this is a nice amalgamation of all the methods that is available to us. Okay. So I again am requesting you to go through the documentation of this package and learn about what we can do. But since these packages are more involved, I will not be going through all of the examples and such, but we have been looking at package documentation throughout the whole of the course. So I hope you guys are well prepared to navigate the documentation now. So let's close this, but let's keep this GitHub page open. Okay, so we can use this package like this. We can wait a few seconds for this to get installed. and we will be also needing this plots package. So let us do all the package installation at the beginning so that we don't have to worry about in the middle of the lecture. So the integrals is complete. Let us install the plots package also. And I have forgotten equal sign here. Okay. So let me quickly check that it is working as expected. So let me do the dummy plot that we have been doing since the beginning. Okay, this is working, but I don't like this theme, so let me change it to 9. Okay, so this is working. Yeah, so let us comment that out and let us begin our journey of learning numerical integrations. Okay, so before starting today's lecture, I just want to say something. The last few lectures that we did, those were slightly on the longer side. Some of them were almost half an hour long. So I'll try to keep today's lecture slightly on the shorter side, okay? So hopefully we'll complete everything within 1.5 hours. And another thing that I want to mention is that if you have seen the last 9 lectures carefully, you will see that there are lots of cuts in the lecture. That's because I have edited those recorded videos heavily so that you can see the final outcome in a very polished way. You don't have to wait for me to go through all the documentation, figure out the errors that I was getting when I was doing live coding. Okay, so every thing like that, I have cut that out. So what I will do for this last lecture is that I will not edit this at all because I want you guys to go through the experience of what it means to do coding and how you can figure out errors when you are encountering them. So it is also a process. I probably should have done that from the beginning, but since I wanted to keep the lectures more intact and polished, I decided to edit those videos heavily. Okay, so with those two things out of the way, let me just write it here that this lecture will be slightly short because the last 3 lectures were over 2 hours. Also, this lecture will be mostly unedited. Okay, so with these things out of the way, let us begin. Okay, so we want to do integration numerically, and we all know how to do differentiations, and that just translates into integrations right away. And here are some known formulas of integration that we all have encountered in our life. Okay, so integration of e to the power x dx will be e to the power x plus a constant. Integration of cos x will be sin x. Integration of 1 over x dx will be log of x. But again, we are not talking about doing these integrations with symbols. Rather, we want to do them when we have them as numbers, right? So let's go again to the basics. We can consider this integration here, which I have written as I, and the integration is from a to b y dx. Okay, so here our y is the integrand, and these are the limits, and this x is the independent variable. So we all know that integration is nothing but doing summations in very small steps, and we can convert this integration into a summation. So here delta x is our discrete steps, which will allow us to work with numbers, and here y is the integrand. So in Julia's term or any programming term, we can write it like this, where this is our current value of the integration I, and with that we can get the value of the next step at I plus 1, like this. Okay, so this will just be yi times delta xi, and since we are using this value to get the value of the integration at the next step, we are calling it Euler's forward method. And one crucial thing that we have to take into account here is that the need of these constants is necessary here, and that is being provided by the initial condition. What will be the initial condition? Suppose you have your integrand y here as an array, and your x is also known. Then what will be the first value of I? If you see that, you can write it like this: y I. Suppose the first value is y1 and delta x1, but you can see that you are missing this I1 value, right? So that should be provided as an initial condition. And when we are providing an initial condition, that negates the need of another this integration constant. So we'll see all of this in action. So just remember that integration is just doing summations in smaller steps, and you can use that kind of approach to do integrations numerically also. So these are our main formulas. I will also write them out in the notebook, and then we will write the functions. One of them will be to integrate a known function, and another will be to integrate a number. Okay. So with that out of the way, let us begin our coding. Okay. So let me just write it here. We have to do integration with numbers. This is needed because the integrand can be very complicated to obtain a exact solution. So how we are going to do it? We will need to remember that integration is similar to doing summation at very small steps, and let me write the formula. So your integration I from A to B of y dx can be approximated as some summation x equal to A to B. So let me write it here also like that. So this is the formula. Here I is the integrated value. Again, for our case, we are going to be storing that in an array. Y is the integrand, and they follow this equation that didx is going to be y. So let me just write them later. Okay, so you can see that when we are solving this integration, this can be written in this form also, which just means that the same concept can be applied in solving ordinary differential equations. Right, and we will see an example towards the end of this video. And another thing we have to remember that the step size when we are integrating has to be adequately small, and an initial condition has to be provided. And this negates the use of or need of an integration constant. Okay, so this is our main formula here. We will be writing this integration I equal to integration a to b y dx in terms of this summations or in small step, and in programming we can write them like this. So here I am just writing them assuming that they will be stored in array, and in Julia we can access array elements like this. And we can write it like this. Right. So here, what is the catch? So if you look at the first iteration, that is I equal to 1, you will see that to get I1, we need to know I0, Y1, and delta X1, right? So here, two things you can do. First is that we can initialize this with a constant because we cannot access the zeroth element of an array in Julia. Array index starts from 1. So we can provide I0 as a constant, which will be our initial condition. Or you can just write it like this. Then in the first case, we will be getting I2, but then also we need this value of I at the first location, and we need to provide this initial condition again. Okay, so you can see that whatever we do, we cannot negate the need of an initial condition. So with that in mind, we'll be using this formula to get our numerical integration values. Okay, so let us begin. So we will be writing a function again. Let us call it Euler forward integration. Just append one so that we can write many functions. So what this will do, this will take a function and integrate that, given a initial condition is provided. Okay, so these can be used as a indefinite as well as finite integration. Okay, so the first thing that our function is going to take is going to be another function which it is going to integrate. Okay, so let me again annotate that if name will be like sine, cos, exponential, polynomial, those kind of things. Okay, and again we can pass anonymous functions here. Then we can give it a limit, say xa and xp. Then we can give the initial condition of I1. Okay, and finally we can also provide it each parameter, which will be equivalent to the delta x, and we are going to fix it for all of the steps. Okay, so we can do one thing, we can just call it delta x so that this becomes easier to identify with this formula. Okay, will be same for all steps, and we will return an array. Let's call it I array, and this array will correspond to all the values of x, which will be in this range in a which is spacing of delta x, right? So let us also return x array and f array. Okay, so this will be our array of these independent variables. This will be the array of the integrand, and this will be the array which has the integration. Okay, so now let us prepare all these arrays. X array, we can use the range function to prepare. It will start from xa, it will stop at xb, and the length is going to be delta x. Similarly, f array, this is going to be just the function acting on the x array, and we will also initialize our I array. Let's initialize with all 0 elements, and this will be same as this, same as the length of this x array. So with that, let us do a for loop. We have to end it here, and in this loop, we'll be using this formula to get our I array values. Okay, so let us do that. Okay, so this function here is written in such a way that this will work on an array and this will produce another array. Okay, but you can write it in such a way that it will work on a number and it will give you a number, so that we can use the dot syntax and use broadcasting on a given array. So we will see another version of this function also. So for here, let us just say, okay, so let us do it like this, that the first value will be this I1, which is our initial condition. Okay, so I plus 1 location, this will have the value I, then this. And what is y here? Y here is just the integrand, which is f name in our case. And we have stored this in f array, or we can call it y also. Okay, so this is going to be, so we can give delta x like x array I minus x array I minus 1. We can do it like this, but since in this case we have fixed that the step will be this, so we can just use this also. If you have irregular steps, then you have to use that particular value. Okay, so this is our function. There are some errors, and we will see how to fix them when we run this function. So I have deliberately made some errors so that when we execute this function, the things that we wanted to show, that we can we can work this out, and we can see this through some examples. Okay, so let's say our function will be a sine curve, and the initial condition will be 0. Okay, okay, so let's do one thing. Let's make it cos. So the integration will just be a sine curve. So first we will plot this. Let us wait a moment for this plot to get shown. Okay, so let us give it a label. Okay, so this is the function that we want to integrate. So now we'll be using this function that we have written, and here this will be cos. This is going to be 0. This is going to be 10. This will be 0, and this is 0.1. So before running it in the plot function, let us first run it here, and you will see that we are having some errors. Okay, so there are two errors. The first is that in this range method, this length cannot be a float value. So what I wanted to say here is that this is going to be the step size. Okay, so if we use that, then it will say that I is not defined. So this was our I array, and this will also be I array. And now there will be another error, which is saying that this is a bounds error and attempt to access 101 element of vector 464 at index 102. So if you see here in this for loop, what will be the first iteration be like? This will be I array 2 equal to I array 1, y array 1 times delta x. Similarly, the last iteration then will be int plus 1 and int, right? So again, I will pause this recording here for some moment, and I am requesting you to check and verify that this will be the first iteration of this loop and this will be the last iteration of this loop. Okay. Okay, so I hope you have verified that this is the case. And the error that we were getting was that in the last iteration, this I array int plus 1, this value was not defined, okay, because our array only contains up to this end, right? So here end just means that it is length of array, okay? So our array is defined for this many elements, but what we're trying to do is we are trying to go beyond that. That's why we're getting a bounce error. So the way to fix it will be to run this loop one less time, okay? Now, if we do that, you will see that our functions are giving results. So let's just plot them now. So I will just use these variables names and let us plot. So I will plot both these y array 1 and I array 1 in the same plot. So you will see that this cost plot that we have done and this y array plot that we will be doing, they should overlap on top of one another. So this is just to check that we are not doing anything wrong in the function. So let's call it the integrand. Let us also plot these and call it integration values, something like that, okay? And if we plot, we'll see that this is the result. So let me delete this cell.
Okay, so one thing that we can do, we can plot this with uh, dash style. Okay, so this will be dash only. Is that visible? No. Let me change the color here to gray. Yeah. And let me do one thing. Let me just change the thing also so that we are working with a so that we are using a light theme. Let us use just the default theme. Okay. And yeah, so this is the plot. And you will see if I make it black, probably you can see that the two lines are overlapping on top of one another here. So this is our cost line and the integrand, and they are just the same. And this is our integration values, which is giving you a sine curve, right? How to check that? We can simply plot sine curve, call it sine, and again, let's make it dark blue. And you will see that our integration values are not completely matching with our sine curve. And here, this was our initial condition, and I chose an initial condition which will match with the sine curve at that position. But then, as we started to do this integration in this for loop, we see that the values started getting deviated from the original curve, right? You can see that this green one and this dark blue one, they are different in these regions. So is that happening? Again, for those who want to think of the answer, I will pause the recording here and I will see you in a minute. So try to think why is that happening. Okay. So if you have thought about it, you should actually know the answer. This is happening because the step size when you are integrating is not small enough. So here I have given it a step size of zero point 0.1. Let us decrease it to zero point 0.01 and see what happens. And now you will see that everything is matching completely. So let me also use a line style of dash here. Okay, so we can see that our cost curve and the integrand are matching. This should match because we are just executing the cost function which just passed through this Euler forward integration one function. That is not surprising that, but you can see that the integration is completely matching with our this sine curve also. If you zoom in, you might see that there are some mismatch in these regions. You can check with these curves. So this green one and this black one, which are the cost curves, and this dark blue and violet one are now the integration and sine curves. You can see that there are slight mismatch here if you compare these two curves. So what you can do is you can decrease it more, the step size. Then let me also increase the size of this plot so that we can see it properly. Let's say we'll make it 600 by 300 now. Okay, so here you can, so this become a bit hazy now. Anyway, so you can check this and you can see that this is completely matching. Okay, so let's do, here there is slight mismatch, and here you will see that this is much better. Okay, so that's how we can do integration. So what we will do now is that we will use this function to integrate some known functions. Okay, and we'll see that whether the results that we are getting is the expected one. So we have seen this. The second example, I will do this exponential and some polynomial integration. Then we'll check those with the known answers, whether they are matching. And then I will write a version of this function which can work on a particular value, not an array, so that we can use broadcasting. And then we can conclude this first section of today's lecture. Okay, so let's copy this for now and let us now plot a exponential curve. Okay, so let me check. We don't need two curves because this will be the same after integration also. Okay, so this is, let's do it up to 5. Yeah, so this is our exponential curve, and let's now do the integration. Let us again use a step size of 0.01, say, and this will all be 2. And here also, you can see that it is slightly below. This is happening because e to the power 0 will be 1. And now if we see that everything is falling on top of one another. Okay, so you can see this is like this, and towards the end, this is slightly deviating. So we can use a smaller step size, and now you see that everything is falling on top of one another. Let me increase the size of the plot again, and let me do one thing. Although we'll be doing the integration with the smaller steps, let me plot fewer points. Okay, so I think this should work. Yeah. So here you can see that everything is falling on top of one another. So here the exponential, the integrand, and the integration values both should be e to the power x, and everything is following a same curve. Okay, so let me just remove these also. We can check that everything is as we expected. So with that, let us also do, so this was an exponential curve. Let us now do e to the power 2x. Okay, and this will again be 0.5. This was 1. So if our function is e to the power 2x, what will be the value of the integration? This will be e to the power 2x by 2, right? And the initial condition will be at x equal to 0.5. So again, I am going through all of them comparatively fast compared to the previous lectures. You are requested to check all this, check that all the initial conditions and those kind of things are accurate. Okay, so let's just pass an anonymous function that will be plotting to the power 2x. Okay, now let us do the integration and everything here. Let me write them the suffix 3, and here the function is going to be this anonymous function. Okay, and let's see the answer. So here you can see that this is our result. Let me again zoom into it. So this black and this orange color curve, they are overlapping on top of one another because these are the same things. And this is the integration, which should be just half of this curve because that's how integration of exponential works. So here you can check if this is around 2 to the power 2 into 10 to the power 4, this should be around half of that, and you will see that this is around 1 into 10 to the power 4. A better way to see this will be changing the y scale to log 10, and then let me change the location of the legend also. So this should be top left, and one thing is happening here is that if okay, the first thing is here you can see that everything is slightly downward. So this is happening because this is offsetted by log minus log 2, and here the problem is that the value at 0 is not defined. So we can start from 0.1 so that we can plot it in log scale, and let us change the initial condition to be zero point 0.5. So it should be something different because now the first point is 0.1, but anyway, we can choose the initial condition to be anything, right? So let us do that. And now you see that this is the answer. And here you can see that the first points are slightly not matching. We can decrease the step size, and this will become progressively better. Okay, so let us do linear scaling, and we don't need this many steps. Okay, so this was another example Okay, so this should be identity actually. Okay, now let us do a polynomial. Say we'll be plotting x cube and we will be integrating that also. So here this integration will be x to the power 4 by 4, and again at 0 this value will be 0. Okay, so let me pass a anonymous function that this is going to be x cube. This is going to be x cube. We will change all the variable names to be y4, and here it should be 0, 0, and let's make it 0.1. And I think I have changed everything, so we can also call it x cube, and I think it should work now. And okay, so now what we can do is we can simply plot this function. Let's plot it in dark blue, and we can see that it is matching with the expected value. So I think with all these examples, you can understand how this numerical integration can be done, and you have grasped the main concept of it. Okay, so let me hide this function and let me just fix it, this plot also slightly. Okay, so I will just keep the codes and just keep the plots and hide the codes for now. And in the next section, we will write this function in such a way that it can work on a particular value. Okay, so let us do that, and everything will throw error because the function name is same, and now everything should work. Okay, so now let us write this function in such a way that we can use this to broadcast on arrays. Okay, so let us fix this. So here we are just going to pass the name of the function, the point it is going to evaluate, and the initial condition, and just the delta x value. So here we will not need these arrays. Similarly, we'll also not be needing these. Okay, and this will be, let's call it I new. This will be the initial condition. This will be the name of the function, and we're going to just return I. Okay, so we want to do this because if you look at this function here, you will see that it will not always be possible to adhere to these limits when we are also fixing the state, right? And we have seen this when we are writing this range function. Okay, so here you can do that. You can choose any x and initial condition for that, or rather, we can call it ix, which is be the value of the integration at this particular position, and we can use this, and we can see how the plot will look like. So I will not plot everything that I have shown here. I will just do one of them. Let's say that I will do this x cube integration plot. Okay. So up to this part is okay. And let me also plot both of them. And this is going to be study for 4 by 4. Okay. So now let us see how we can use this function here. So we can call this function. So let us do it here first. So our function is this, and we want to evaluate it at, say, from 0 to, so suppose let us do it for one value now. We want to evaluate it at 0, and our initial condition is going to be 0, and delta x, let this be 0.01. Then this will give the answer just that this is 0. Now at 1, this is 0.25, and the answer will be this. Okay, so here you can see the problem that we have to take care of, that the initial condition for each iteration has to be given, although we just want to specify it just for the first iteration, right? So we can bypass that by using these to be zeros for all the case, and then just we will just add the array to it in a shifted way. Okay, so what do I mean? Let me just say that we want to do this for 0 to 5 at an interval of 0.01, and we will broadcast this. So this is our answer. So here, since we are making this to be 0 forcefully, this is only giving us this part. So for each case, we have to add this to our answer. So for the first point, we will add the initial condition I1. The second point, or the for the second iteration, we will add I2. What I2 is? I2 is I1 plus the result of this function for first point. Similarly, for third point, we will need to add I3, which will just be I2 plus result at second point, and we can write it as we can use this equation and we can write it as this plus result 2, right? Similarly, you will see that for the fourth point, we will be writing it like this. This will just be okay. So you will see that what you are doing at each step is just adding the result of this expression. So adding like this is called cumulative sum, and we can use the sum function here to do this. And with the cumulative sum, we will be adding this initial condition. Okay. Since we are already passing the initial condition here, we can just get the result like this. So this is going to be our integration result. So what you can do is I can comment this out here and I can use this here to plot. So we can remove these and this also, and we can plot these and this. Okay, let me remove this also and let us do the plot. And you'll see that this is our actual result, the blue dark blue curve, and this dashed green one is the integration values, and you will see that everything is matching with the result. Okay, so now let me show you another way of doing integration, that is the trapezoidal rule. So I will not talk about this in a great detail. So what this state is that the integration of something from say A to B of a function say fx. Okay, so we can approximate this integration like this. And the text is not being generated. Yeah. Okay, so suppose we have this definite integral of fx dx from a to b, then the result is going to be b minus a by 2 fa plus fb. So this is called trapezoidal rule, and these are part of some approximation schemes. So you have Simpson's one third rule, Simpson's 3 by 8 rule, and another one is, I think, Boole's rule. And in general, these are called Newton course formula or Newton course quadrature rules, and they are used to evaluate this kind of definite integrals, okay, numerically. So these are quadrature formulas, and there are two types, closed and open. So you can learn about them uh, on your own. So I just will say that these Newton course formulas, they can be very easily derived also. And this trapezoidal rule is for Newton course formulas when we are dividing this integration, the definite integral, only taking the endpoints, two endpoints, right? So in Simpson's one-third rule, we will be taking another point in between. Then 3-8 rule will be taking 4 points, 5 points like this, okay? And this will be called a closed formula when we are going to use the boundary values. So this x equal to a and x equal to b, those will be used. Then that is called a closed form. If those are not used, then that is called an open form. So in this lecture, I will not go through all of these details. I will just show you this trapezoidal rule, and I will also show you how this can generate some very good results. Okay, so this can be very effective when you are trying to find the area under a curve. Okay.
So let me write the function. Let me call it trapezoidal integration 1, and this will take the function, name of the function, the limits a and b, and I will pass another argument n, and we will see how n is going to be used. Okay, and this will return the value. This can be used to plot something also. And we'll just see for a definite integral whether the results are given correctly, and we'll also do a plot. Okay, so with that, I think we can close today's lecture, and I will later share one of the problems. So we'll solve a coupled ordinary differential equation, and with that, we'll close today's lecture. So let me remove all of these. Okay, okay. So the return value here is going to be b minus a by 2, and then this, right? And let me also give this in a default value. Okay, so let us integrate the sine function from 0 to pi. And okay, sorry, this should be like this, and we are getting this result. Now, what is the expected result? The expected result is 2, because we know that integration 0 to pi sin x dx is 2, right? But then our function is giving us a very bad result. This was supposed to be 2, but we are getting 0. And we can see that this is correct because this f name
A and f name B, which is just evaluating the value of the sine function at 0 and pi. Both are then are giving the result 0. So if you add them, this will be 0, and if you whatever you do multiply with anything, the result will be 0. So why this is giving wrong answer? Because we are just using this formula like this. So this is just an approximation, right? This is just an approximation. And for this approximation to be true, again, we have to make sure that the step size that we are taking for this integration, that has to be adequately small. Now, what is the step size here? You can see that it is doing this whole integration from A to B in one step. So the step size here is pi, and that is not small. So what we can do is we can divide this integration into multiple parts. Okay, so we can write it like this, where this will be this plus this. So we can divide the integration in two two parts. One will be from A to C, then it will be from C to B. And you can check then that the answer will be this plus this. Okay, so this is the correct answer now. So now you can see that if we divide it into two equal parts, then also the step size is not very large, right? So what we can do is we can keep on dividing it into sub steps so that the step size becomes adequately small. So here, this right hand side will get accordingly changed. So if we divide it to say from A to C1, then C1 to C2, C2 to C3, C3 to C4, then it goes on, and say after 100 step, it will be C100 to B. And then for each of these steps, we can use this formula separately. So this will be C1 minus A by 2, then F of A plus F of C1, then C2 minus C1 by 2, then F of C1 plus F of C2, and it will go on like this. And when you do it like that, then the step size will be small enough that the approximation will be very good. So that's what I have kept this in parameter for, and that will just tell us the division of the steps in between. So we can see that by default we want to divide it into 1,000 steps. So how will we do it? So we can use the range function. This will start from A in that B, and our length will be N. So this will be the subranges. Okay. Now what do you want to do? You want to use this value formula for each of these consecutive ranges. So we can use a for loop now. This will be 1 to n, and we can initialize the value to be 0, and we can increase it at every step. So here I am just modifying it at place, and like this. And you can see that if this formula has to work correctly, we have to start from the second uh, value in our loop. Okay, so now let us run this. And with the new function, you can see that the value of this integration is now 1.9999. So you can see that this is giving us almost accurate result. So we can check that this is the approximate symbol, which will check whether this value is approximately equal to 2, which is giving false. So we can increase the n to be, it was 1000, so let us do 10 to the power 5, and you will see that it is now returning 2. And the value is almost to 1.9999678. 9 points after the decimal is 9. So this is extremely accurate. So you can see that how this simple approximation can be subdivided between this integration range, and this can be used to get the formula, get the integration of a definite type, right? So similarly, you can also learn about this Simpsons one-third rule, Simpsons three-eight rule, Boole's rule, this kind of things, and Newton's code formulas in general. Okay, so I will not go over all of these one by one. You can look up these in any book or any in the Wikipedia. The formulas are simple enough like this. You have to just write the function in Julia, and I hope after all these many lectures, you are well equipped to do so by yourself. So check that these all these formulas also are giving you accurate results. Okay. So with that, I will just show you how to use this function to plot curves, and then we'll go to solving this coupled ordinary differential equation. So here, if you want to plot it, we can use this fact that, let us call our integration I, and let me just copy this. Okay, so this is equivalent to this thing, right? So suppose I want to, after doing, want to plot the values of this integration, then I can do it like this, right? So I can get the value of IB at the desired locations, and this integration can be approximated with this trapezoidal rule, and IA is my known point. Okay, so we can see an example of this. And I just want to mention one thing, that when you are doing this integration like this, it is very easy to see that how this can be extended to get area under the curve. For example, if you have a curve, say x square, then you can simply do the integration, and you will, within this range, you will get the area under the x square curve. Similarly, if you have multiple curves, you can do the integration separately and subtract them to get the area enclosed by those two curves. Okay, so you can try those out by yourself, and let me just do the plot here. So we'll be again doing this plot. So let me just plot the known values. Now, suppose you want to do this integration in this range. So let us call this something like desired range, which will be from 0 to 5, suppose in the step of 0.01. Now, for each of these, I want to get this IB value. So let me just define one array. So everything is zeros now, and we can use a for loop to populate this array. So this will be just like this, plus there will be the value at this position, right? So we can do that by starting the loop from the second array index, and the first one, which is this I1 minus 1 in the first iteration, will be our initial value. We can set it to be 0 for this case. And here our function is going to be this one, and the values will be from I minus 1 of desired range to I. And you can just say that we will be doing 100 steps for now. Let us run. This gives me one error. Okay, this has to be I array, and this also has to be I array. So it is running. So let me do the plot now. So we will plot our desired range, and I add a, and let us give it a label that this is integration using trapezoidal rule. And we can see that these two plots are overlapping. So to see it better, we can again give the line style to the dash dot, and we can see that this dash dot curve in green and this dark blue curve, they are completely overlapping with one another, right? So you can check another thing, that if this value of n is 1, okay, if we just do this 2, and you will see that if I make it 2, then also it is giving very good result. So let's do it 0.1. Let's do it 6. And you can see that still this is following the curve. So you can get an idea that how good this approximation is. And it is only doing this approximation by taking the n2 points. This Simpson's one third will take 3 points, so n2 points and 1 point in between. Then this 3/8 rule will be taking 4 points. This Boole's rule will be taking 5 points. So those will give you much better result. So with that, I think we can stop learning about this numerical integration now here. And the problem that I want to solve, again, here, that problem is called Lorentz attractor. So this will be given by these coupled differential equations, and we can get this kind of simulations. So let me get the link of this image. So this will be a Lorentz attractor, and the equations, I think, okay, this is wrong. Okay, so you can embed these graphics also in Markdown. The equations of this Lorentz attractor is given here, and we'll be solving this for these values of the parameters, and we'll assume that the initial conditions are 1 for both x, y, and z. So let me see that, okay, this is another image. So instead of typing out all those equations, I can just give the link here, and This will show the equation also. Okay, so this is not completely visible, but you can see the equations. Okay, and this will be our solution. So this is the final goal of this course, that so that we can solve this coupled ordinary differential equation using all the knowledge that we have gathered about numerical computation, Julia functions, everything. Okay, so I will do this. I will not be doing a lot of commentary when I'm writing the function, so just bear with me, and we'll be getting a similar kind of plot after we have completed our coding. Okay, so with that, let us begin the last problem for this course. But before doing so, let me also introduce you to this other uh, integration method. So the thing is that every problem will be different, and some methods like these quadrature rules, this trapezoidal or Simpson's one third, or this Euler forward method, these will be suitable for some set of problems, and for other set of problems, you will not be able to use those. So for these, I have, sorry, not me, others have developed many other ways to do this numerical integration. One is leapfrog method, which is very good to do stability analysis and generating orbits, satellite orbits, those kind of things. These quadrature rules will not work when your integrals have the limit to minus infinity to infinity or 0 to infinity, those kind of infinite limits. There we can use these Gauss-Hermite or Gauss-Lagrange quadrature rules. Similarly, we have Monte Carlo simulation using quadrature. So these all you can learn when you are solving more involved problems. Okay. And finally, uh, these are some books that I will recommend you guys to follow if you want to learn about numerical computation more. So this book is written by a professor in my institute, and this is mainly for Python users, but still the concepts about how to do numerical computation, those interpolation, integration, those kind of things, the theory behind it that is explained beautifully here, and those things will be same for everything, right? Just the implementation of these methods in different language will be slightly different. So that's why I also taught you guys the essence and the basics of Julia with great detail so that you can go through any of this book and you can take any of the approaches that we have not discussed and you'll be able to implement that in Julia. Okay. So you can look at this numerical computing with MATLAB book also. This is also a very nice book. So I have personally read these two books and I have enjoyed it. But this is another book that a lot of people recommend. So if you have time, you can go through this book also. So if you want to know more about this, you can search the internet. Wikipedia has very good articles. If you prefer reading it from a book, then you can use these references. Okay. So with that, I thank you all for joining this course. And now we will solve this problem and close the today's lecture and complete the course.